Good morning, good afternoon, good evening, everybody, wherever it might be. It is my great pleasure and honor to introduce today my friend, colleague, and collaborator, FRANCESCA ARICI. It is always a pleasure to work with her, but I have to warn you that she is a tough cookie as a collaborator, because even if you're a super strong mathematician like Michael Atiyah, she will still be the first author. So I seriously considered for a while to removing H from my surname, because it's silent in French, silent in Italian, and then I could beat her alphabetically. But anyway, I didn't do it. So ladies and gentlemen, silly jokes aside, without any further ado, FRANCESCA, the floor is yours, the Zoom is yours, take it away, prego.
Thanks a lot, Piotr. And thanks to all the organizers for having me today. So this joke just reminded me that once I was called for an interview from the local newspaper when I was in Nijmegen, local university newspaper, and they wanted to understand if I had ever had any advantage having a name that starts with A in mathematics. And then I explained, no, because we publish alphabetically, so everybody knows that you're not the first author.
Exactly. Exactly.
But it was very difficult to have, and then they talked to another colleague of mine that started with Z, and of course they explained the same thing, but yeah, so if we were in another science, it will make a difference, but yeah.
Yes. Okay.
So I'm very happy to report on, well, as the title says, on this work on split extensions and Kk equivalences for quantum projective spaces that it's joint work with Sophie Mikkelsen, which I just saw in the audience.
Yes, she is in the audience.
Yeah, and it's on the archive. So here's the archive identifier. So this is a work somehow motivated from noncommutative topology. Yeah, let me also give a disclaimer now that it's basically the first time I try to give a talk like this. So if something, I hope this goes well. I usually prepare slides and annotate small things, but since this seminar is a bit longer than usual, I thought it would be nice to pretend that I have a blackboard. So yeah, let's keep an eye on the time. I'm supposed to finish at
a quarter to 6.
7.
Sorry, 7, of course.
Okay. So yeah, roughly 1 hour and a half. Okay.
Yeah.
So the motivation for this work comes from noncommutative topology. In particular, as the title of my talk says, we were interested in study the K theory. Well, the K theory of quantum projective spaces, and I should stress these are the Waxman-Soibelman quantum projective spaces. Through Kk theory. And the goal of this paper is was to construct an sorry, I'm talking over myself. So the goal was to construct an explicit Kk equivalence. And this started actually like 2 weeks before the pandemic. So I had contact with Sophie about this question for a while, and then she came to Leiden to do her environmental exchange, I think it's called. And then after 1 week, she had to flee because Denmark was closing the border and we were going into lockdown. So this was a work, I guess, one of the first, maybe my only work that was entirely conducted online, except for a couple of conversations that we had in person when we started this off. So it's a pandemic work. And so I should also stress at this moment that there are various ways of knowing that such a Kk equivalence between the algebra of the Waxman-Soibelman quantum projective space and their classical counterparts, so the continuous functions on CPN. It is known that those Kk equivalences exist, but what we were focusing on in our work was finding something that was explicit. So explicitly constructing the Kk cycles that implement this equivalence. So I will therefore start by introducing the main characters. So this is the plan of the talk. The first parts will be indeed about the Waxman-Soibelman quantum projective spaces. And in particular, we're interested in the graph algebra picture. So the way you can see this, there are various ways in which you can look at this quantum spaces, and one of them is by seeing them as graph C-star algebras. And the second part of my talk will be about Kk theory and Kk equivalences and what we know, what we can deduce using the theory. So I will briefly recall what Kk theory is and discuss some examples of Kk equivalences, and in particular, the connection between split extensions and Kk equivalence. And the final part of the talk will be indeed about proving this Kk equivalence explicitly. And this we did by constructing splitting and deducing Kk equivalence. So construction of a splitting for a certain exact sequence that you will see in a second, and the proof of Kk equivalence. So let us start with part one. So I will introduce the main characters in this talk, which are this Waxman-Soibelman quantum projective spaces. C of, and we denote their sister algebra as C of Cp and Q for n greater or equal to 1, although n equal to 1 is just a complex number. So that's a trivial case. Okay, so these are C-star algebras, so they can be thought of in the philosophy of non-commutative geometry and topology as quantum topological spaces, so as an algebra of functions on some virtual space. And the nice thing about this object is that they have a quantum homogeneous space structure. They actually have two different quantum homogeneous space structures. So the first one is that they are quantum homogeneous spaces for a U1 action on the Waxman-Soibelman odd spheres. Again, in analogy, this is in analogy with the classical case, so it's possible to realize C of Cp and Q as the fixed point algebra for a U1 action on the algebra of continuous functions on the Waxman-Soibelman sphere. And there's a further quantum homogeneous space structure, which is that of for an action of the quantum group UQN on SUQN plus 1. And this is again in analogy with the classical case. So classically one can realize projective spaces as homogeneous spaces for this of this form. But for this will come back later. So I will see more on this later, especially in relation to the fact that we do know that these sister algebras are Kk equivalent to their classical counterparts, and this comes from this particular quantum homogeneous space structure. All right, so let me first focus on the latter, so on the U1 action on the Waxman-Soibelman odd spheres.
Sorry, may I have a question?
Yes.
So these two constructions yield the same sister algebras or different ones?
No, it's the same sister algebra. So it's two ways of seeing the same sister algebra as the
same. You mean star isomorphic? Yes.
Yeah. Yeah.
Okay.
Look, Adam, it's very simple. This is UQN instead of SUQN. If you would put
exactly.
an S here, you would get this sphere as an intermediate quotient.
That's what's going on.
Yeah, I mean it's if you would put S here, you would just get this sister algebra. But because you remove the S, it means that you divide by additional circle. So you take like fixed points here, okay?
Yeah, so this is what I...
Okay, thank you.
What I just noted here. So it's the other, it's the you go through, by going through the sphere, you get this homogeneous space structure for this other one. So, but I will want to focus on the latter also because of the graph algebra picture. Oh, sorry, on the former, I should say. So we take Q between 0 and 1. And we define the Waxman-Soibelman quantum sphere C of S2n plus 1q is the universal C-star algebra generated by n plus 1 elements that we denote Z0, Zn. And those are subject to the following relations. So Zi, Zj is equal to Q inverse Zj, Zi. Then we have Zi, Zj star is equal to Q, Zj star, Zi. So this is for I different from J, and this is for I smaller than J. And then we have the two sphere relations. So on one side, we have this one, Zi star, sum from 0 to n of Zi star is equal to 1. Then we have the Q-deformed sphere relation, which is that Z star Zi is equal to Zi star plus sum. And now we have to sum from J equal to I plus 1 to n, 1 minus Q square Zj star. Okay, so these are the commutation relation in the quantum spheres, and you see that there is a normal element, the one with I equal to n. There are different conventions, so these relations may surface with the indices flipped in the other direction and the Q's going the other way around, but this is one of the presentation of the C-star algebra as universal C-star algebra. And of course, if you put Q equal to 1, you do recover the continuous function on the commutative 2n plus 1 dimensional sphere. And
could you explain how this construction is related to the Podlesh sphere?
Oh, well, which Podlesh sphere? You mean S2?
Okay, so here the dimension is...
These are odd. So the Podlesh sphere is a particular case of, well, the Podlesh sphere with only one parameter is a particular case of the convex projective spaces that I describe here. But the other Podlesh spheres are not, as far as I understood, related to those.
They are just
okay. Sorry.
But you are right. They are not explicitly in a construction because you talk about odd spheres, and exactly. This is an even sphere. But you see, when you take this normal generator here, if instead of killing it, you declare itself adjoint. Oh yeah, then you get even spheres, and but then what you will get for S2. So you take SUQ2 C-star algebra. Okay, you take this Waxman-Soibelman in dimension 3. And now declare this normal generator self-adjoint. And that what will happen that you will get the equatorial Podlesh sphere. Yeah, exactly, yeah. The one with a circle inside, okay? And that's also isomorphic to CP1Q, which I will define. Exactly, but you will get the standard Podlesh sphere, the minimal initialization of compact operators here as CP1Q. Yeah, it's a CP1Q indeed, yeah. But that, I mean, the other ones with the other parameters, I'm not sure. Oh. No, that's yeah. But the sphere, not the projective space. Yeah, the spheres. No, I just meant that for and so the two sphere is a projective space, so it's CP1Q. So then we define C of CPNQ to be the C-star algebra of invariance under a U1 action. So we consider C of S2n plus 1Q. And we look at the invariance, and the U1 action is the one that maps as at I to omega times that I for all omega in U1. And this C-star algebra is generated by element of the form Pij. So those are the Zi star Zj. It's easy to see that they're invariants for this action, but actually all the invariants are of this form. Plus relations that you can deduce that are deduced from the ones above. So I'm not going to spell them out. There's a lots of Q's going on. But what you get is that the Pij's are entries of an
n+1 times n+1 projection. So in particular, they also satisfy some Pij, Pjk is equal to Pik, and there are Pij star is Pji. Okay, so this is the definition of the sister algebra of CPNQ, and indeed for n equal to 1, this is C of CP1Q is the standard Podlesh sphere, which we know
that's a
indeed.
quick question.
Yeah.
And so like, why are the like order 2 elements sufficient to describe the quotient
Yeah, because of the commutation relation. So you can always move around.
So like why, for example, how could we express some Zi like in terms of the Pijs?
Well, they have to have degree 0. So you declare the Zi to have degree 1, Zi star to have degree 0. This comes from the
it's
from the action.
One.
So you look at the fixed point. So then you have to do because of the commutation relations, you can always move all the stars on one side.
Yes.
Yeah.
And
so it's Gröbner base is a type argument, but.
And so do you say like that, like any other like for example, like higher powers, because of the commutation relations, there's some cancellation or something like that?
Well, because of those commutation relations,
But it's just generated by elements, yeah.
I think this, yeah, for instance, this one, you can always move all the stars on one side and all the eyes to the other side, or you can, if they're all, sorry, maybe the other way around, if you have, you can reduce anything that has degree 0 with respect to the grading coming from the U1 action. You can move it around, move the stars around in a way that you get products of these Pijs. But it's, yeah, it's just I would say diamond lemma type argument that you can use here.
I think I get it.
Yeah, okay, thanks. Okay, so interestingly, in 2002, Ong and Szymanski proved that the quantum sphere, that both, there are many, and there is one for every n. So the quantum spheres C of S2n plus 1Q and the quantum projective spaces quantum complex projective spaces are graph sister algebras. And this allows one to infer a great deal of information from those about the structure of the sister algebra. So let me just recall what a graph sister algebra is. So a directed graph E is a quadruple E0, E1, R, and S, where E0 and E1 are countable sets of vertices and edges, and R and S from E1 to E0 are the range and source map. So they're the maps that indicate from where and to where an edge goes. So for instance, if you have V, like we have two vertices V and W, and you have an edge E, you're connecting them and going this way, then the range of E is W and the source of E is V. And I should remind you that in the Australian convention, arrows go the other way around. But this is the convention we're going to use in this talk.
Well, these guys are upside down, you can understand.
Yeah, I mean, also water turns the other way around there, right?
Exactly.
So not surprisingly, things go the other way around there. So, and here I put no assumptions on the graph. I just assume that it's directed. So no row finiteness or no sink assumption. So let me just first say that the vertex in the graph is called regular. Oh, my pen is acting up. No. If S inverse of V, so the collection of all the edges that start in V is either finite, is finite and non-empty. So, and the vertex is called singular if it's not regular. So if there are no edges starting from the vertex, we say that V is a sink. And if there are infinitely many edges starting from that vertex, then we say the V is an infinite emitter. So when we are talking about regular vertices, we are excluding both infinite emitters and sinks. Okay, and now comes the definition of the graph algebra. So for E, a directed graph, C star of E is the universal C star algebra generated by projections PV, one for every vertex, and partial isometries SE, one for each edge, satisfying the following conditions. So first of all, the projections are orthogonal if they're different, if the vertex is different. Now we have a similar condition on the partial isometry. So SE star SF is equal to 0 if E is different from F. And this has to do with the fact that we want to be able to compose the partial isometries when they belong to a path that is, that doesn't break somehow. And then there are these Constrictor relations. So SE star SE equals the projection onto the range of E. And SE star as a projection is bound by the projection onto the source of E. And this is a condition that works specifically in that you have to put specifically in the non-row finite case. And finally, we also have this condition that PV is equal to the sum over all the edges that start in V as SE star for all V regular. All right, so these are the 5 relations that you have inside, and this in particular are the Constrictor relations. And they're called like that because the Constrictor algebras are a special case of this construction. There the graph is finite and there's up to one edge between each pair of vertices.
I think you should include number 5 as a
you're right. You're very right. I was thinking the same, but luckily that's the beauty of having a tablet. Yes. I can do like this. So yeah, so the last 3 are the Constrictor relations. Okay, so and given this description of the graph algebra, there is a canonical U1 action called the gauge action. Which is defined as mapping PV to PV and SE to omega SE for all, well, omega in S1. and then extended by universality to the whole of the C-star algebra. So once you have it for generator, you can use it by universality, you can extend it. So let us look at what happens in our particular case. So this again, as I said, is due to Wong and Szymanski. So they proved that the odd dimensional spheres, actually in the paper, they also have the even ones, are graph algebras for a certain graph. So C of S to n plus 1q is isomorphic to the C-star graph C-star algebra of a graph called that they call L to n plus 1. I will tell you in a second what this graph looks like. So L to n plus 1 is a graph as n plus 1 vertices and one edge. So let's call this vertices V1, Vn plus 1, and one edge between Vi and Vj. Well, we should say from Vi to Vj to be clearer. Whenever I is smaller or equal to j. So let me draw, for instance, L7. So in that case, we have 4 vertices, V1, V2, V3, V4. So we have loops at every vertex. And this comes from the fact that we also, in our condition, we also put the equal sign. Then we have those edges that connect successive vertices, and then also we have the ones from V1 to V3, from V2 to V4, and then from V1 to V4. So if you look at the incidence matrix of this graph, it's an upper triangular matrix with all ones. That's the incidence matrix. Which is a matrix that tells you, so there are particular Constrictor algebras you can see from here, because they're all zeros and one, the entries.
Sorry, is it somehow related to the CW structure of the complex projective space?
Yeah, pretty much, yes. And yeah, well, we've been working on this in another paper with Piotr and Francesco and Mariusz. So there is a connection here, yes.
Mm. Okay, thank you.
So this is the graph algebra of the quantum spheres. And now to, what is interesting is under this isomorphism that you have between C star of L to n plus 1 and C. Okay, the proof that these are actually isomorphic is not easy. It requires homomorphic continuation argument. But the first thing that you observe here is that they're all isomorphic for different Qs, as Q varies between 0 and 1. And the reason for that is that the graph algebra relations do not contain the Q. So this is the first important consequence of having this graph algebra picture. And the other thing is that under this isomorphism that you have between the graph algebra and the Waxman-Seuberman spheres, the gauge action corresponds to the U1 action that I described above.
Francesca?
Yes.
Can you describe like some of the, is there maybe some concrete relation like for some Q, or like in one way or the other way only? Like what?
Yeah, you need to, so you would have to write down a power series expansion and then continue it. So the proof is quite, the construction is, how do you say? So there's it involves infinite sums, the explicit form of this isomorphism. So it's not that obvious. I was, yeah. Think
so in one direction, but maybe in another direction. Like
no, in both. In both is both. Look, yeah. Alex. Look, think about the quantum disk of Klimek-Szymański. This is all the Teplitz algebra, just a different presentation. And Klimek-Szymański give it by weighted unilateral shifts, whereas the Teplitz algebra by the work of I forgot his name, is just generated by a single simple isometry. So this is just the universal isometry. This is just unilateral shift.
It's Coburn.
Yes, Coburn. Thank you, Francesca. Coburn. Yes. Yeah. And then already in this extremely simple case, it all boils down to proving that the quantum disk sister algebra is graph sister algebra. Basically, what you have to do, you have to prove that the sister algebra does not depend on Q. So running Q equal to 0 gives you isomorphic sister algebra. But this is, as Francesca said, is all done by analysis. These are non-algebraic correspondences. You have infinite series. Even in the simplest case, it's complicated to write it down. And it's really worth emphasizing, and Francesca did it, is that what Hong-Szymański did was highly non-trivial. So that's not so obvious. Oh, okay, that's just the same sister algebra. Somebody else discovered it, and all we do just give it a different presentation. No. There's actually giving it a different presentation was very hard. These are non-algebraic arguments, and she cannot answer your question within reasonable time.
I also remember when I was studying that paper, I was quite impressed they had to come up with that. One was like, where did you find this? I mean, yeah, it's quite, so it's not that transparent actually to see that.
So I guess this wouldn't even be, so I guess there wouldn't even be an isomorphism on the level of the Leavitt path algebra and on the star algebra like Jim. I see. That's exactly like that. So only as soon as I see. Yes. Thanks.
Thanks for asking. Yeah, but what is nice is that the gauge action that you have on the side of graph algebras actually corresponds through this isomorphism for some magical reasons to the U1 action that I described.
Sorry, just one more question. Did I understood correctly that without this theorem, this identification with the graph sister algebra, it would be very difficult to prove that for different Q you have isomorphic sister algebras?
No, not difficult, but lengthy, I would say. So once you guess how to, it's an analytic continuation argument. So when you look at this limit Q goes to 0, you can work with analytic functions and show that there is the isomorphism, but it's not that easy to prove, to come up with the form of the isomorphism. So I don't know if you understand. Yeah, it just involves an infinite sum, and it's quite,
Okay, so what I meant is that somehow the proof, suppose that we forget about this graph sister algebra, and still showing that for different values of Q, you would get.
You could do it with representation theory though, because you also know it for SUQN that they're all the same. That the representation are the same as Q equal to 0. I think maybe this was even in Waxman and Soiberman. So,
yeah, Francesca, absolutely right. I mean, you would have faithful representations of two sister algebras, and then you'll find unitary equivalence intertwining them.
Yeah.
But in a sense, you are right, Adam, that this is exactly what helps. Instead of doing some strange things and proving, okay, for Q and Q prime, this sister algebra is isomorphic, we say that whatever Q we take, it's isomorphic to a graph sister algebra. That definitely helps. Yeah. And I don't think it would be much easier to prove Q prime. Basically, this graph sister algebra is the case of Q equal to 0, roughly speaking.
Yeah.
Okay. So these two problems essentially boils to the same problem, yes?
Yeah.
Roughly speaking, yeah.
Yeah.
Okay, thank you. That was exactly what I meant. Okay, thanks.
And so so using this gauge action, Hong-Szymański proved that the continuous functions on the CP and Q, so on this Waxman-Soiberman projective space, are the invariant for the gauge action of the sister algebra of this graph that they called L2M plus 1. But this algebra is also graph algebra itself. It's a graph, and the graph I will describe below. And this requires a notion that I'm not going to dwell into, but it's a construction on its Q product of a graph with a group, and the corresponding graph that, let me write it for S7. So it has the same number of vertices. So it has, so Fn as n plus 1 vertices. And now it has infinitely many edges between, well, from, again, Vi to Vj, or I smaller than j. So in this case, in the case of F7, we have infinitely many edges between successive vertices. And then we have infinitely many here and infinitely many here.
And this is the countable infinity.
Yeah, exactly. It's a countable infinity, and it has to do with how, with following infinite paths around in the graph F7 somehow. Because of this loop here, you get very long paths. But this is just a heuristic argument. You should look at the proof. But this in particular means that this graph F7 is not row finite. Well, F2 Fn is in general not row finite. And it has, and all the edges, all the vertices are singular because they're either infinite emitters or sinks in the case of the last one. So this I should call V4 in this case, W. All vertices are singular. So Wn plus 1 is a sink, and the others are infinite emitters.
Sorry for interrupting again. I have maybe stupid question, but is it somehow surprising that if you take some graph and then you somehow amplify every edge to infinite number of edges, you would get the same sister algebra, or this is something which is common in this theory?
You don't get the same sister algebra. So this is the fixed point algebra, sorry, for a U1 action. So this is now now CPNQ, yeah.
Okay, okay.
So, and
so sorry.
No, and the reason why these edges amplify to infinity to infinities is because of the presence of these loops. So you're looking at paths of a certain length, and if you look at infinite paths, then there are infinitely many ways of having an infinite path between V1 and V2, depending on where you first loop around. So depending at which point you put this one, it gives you infinitely many options. So this is a very singular graph, but nevertheless, they prove that this is a graph sister algebra, and we can use the theory of graph sister algebras to say something about this sister algebra. So the first thing that we can do is compute its K-theory. So we can compute the K-theory of C of CPNQ as a kernel and co-kernel of a certain matrix. So if the graph is row finite, there is a way of computing of a certain map, I should say. For a row finite graph, it's the K-theory of the sister algebra can be computed as kernel or co-kernels of 1 minus the transpose of the incidence matrix. Here, because the graph is non-row finite, we need to use a different construction. So there is a map that it's called K of E. And it's the map from the set of regular vertices. So from the free Z module over the regular vertices, sorry, to the free module over the set of vertices that maps a regular vertex to this sum, to the sum of the ranges of edges that start in that regular vertex. And this we can do because the vertex is regular, otherwise this sum wouldn't be finite. And then we subtract V itself. Now, what is interesting is that because here, there are no regular vertices. We actually have a map from 0 into Z to the n+1. And in particular, we get that the K1 of C, P, and Q is Z to the power n+1, and is 0. And K0 of C, P, and Q is Z to the power n+1 because it's the co-kernel, so it's the image is 0, so it's all of the image. It's all of the codomain of the map. So by seeing this C-star algebra as a graph, C-star algebras for this graph, this non-row finite graph that I wrote here, you can compute the K-theory groups. And interesting, these are they agree with the classical K-theory groups of the complex projective spaces. Okay. Now we can say even more about this graph. So we can say something about their ideal structure. So in the theory of graph algebras, if the graph is row finite, there is a correspondence between a hereditary saturated subset of the graph and gauge invariant ideals. Now this correspondence is no longer one-to-one when the graph is non-row finite, but given hereditary and saturated, and I will say in a second what this means, subset of the set of vertices let's call it H. We get an gauge invariant ideal IH, and moreover, C-star of E modulo IH can be realized as a graph C-star algebra as well. And this is it's a graph that is called E modulo H. I'm not going to describe the construction, but I will tell you what this is in our case. So let me recall what hereditary and saturated means, however, because that's interesting for our applications. So we say that, oh, I didn't want to do this. So we say that H subset of E0 is hereditary and saturated if the following two conditions hold. So the first one is that for V in H and W another vertex, if there exists a path from V to W, then W also belongs to the set H. And the other condition goes the other way around somehow. So if you have an element on the vertices of your graph, which is regular, so stuff. So there is at least one edge living from it, but not infinitely many. And such that for all E in E1 with source in W, then the range is in H, then this W must be in H to begin with. And when we look at the graph of the complex projective spaces, we see that there is one hereditary and saturated subset, which is just this vertex here, V4 or Vn. So the singlet for Fn, Vn plus 1. So the singlet as a subset of the set of vertices of Fn is both hereditary and saturated. meaning that, well, there is no path from W to anything else. So the first condition is true. And for the second condition, there are no infinite, well, we have no infinite emitters. And so in particular,
now we have only infinite emitters, but this condition is so regular.
We only have infinite emitters and sinks, so this condition is also empty. So this is the only hereditary and saturated subset that we have in this graph. And
Francesca, do you mind if I make a quick comment at this moment?
No, of course. Okay. Please go ahead. I can also drink something.
Yeah, I'm sorry I interrupted so many times, but this is so much fun. So you see, this is a misleading way, because this is in fact the subgraph. E mod H is not the quotient graph, it's a subgraph of
E. It's a subgraph.
But just in the books, this is why I refuse to call it a quotient graph. It's in fact the subgraph in which you are killing some part related to this hereditary saturated subset, and then everything is nicely described by this ideal.
Yeah, so maybe there should be a set minus instead of a quotient.
Yeah, exactly. Yeah, I think roughly speaking, what you're doing is this one, except that you have to also remove all edges which end in H. Yes,
exactly.
And another thing is that if you look, and it came to me as a kind of surprise. I don't know how well known it is in graph algebraic community. So Alex is my witness here, but during my lectures 1 year ago, and this was actually a question asked by Xiao, who's also in the audience. He asked the following simple question when we're studying the properties of hereditary subsets. Okay, so I have V0, and I have a family of hereditary subsets of V0. I take all hereditary subsets of V0. And when you look at properties of this, you realize that it gives you a topology. And moreover, this topology, which you can prove, this is exactly the right topology. This is the Alexandrov topology that is given by the natural order that you have among paths. So that's brilliant. And moreover, if you want to define a connected graph, which is kind of tough because you have to say, okay, a graph is connected when there is an unoriented path between any two vertices, right? But you have to say what an unoriented path is. And so this is a bit clumsy and combinatorial, but lo and behold, if E0 is connected in the sense of hereditary topology, then the graph is connected in a combinatorial sense. And I find this amazing, and somehow nobody taught me. I found it because Xiao asked me a question.
That's very nice. Yes.
Thanks for the reminder.
Yes.
Okay, thanks.
Yeah, so what happens is that in this case, if you remove the last vertex and all the edges that go there, you get that, okay, I'll use the quotient symbol. This is actually Fn-1. So it's the complex projective space of one complex dimension less. And on the other end, this is just the idea that is generated by the projection onto this Vn+1 is isomorphic to the compact operators. So what you're left with is that you get an exact sequence of C-star algebras, or an extension, if you prefer, where the algebra in the middle is the C-star algebra of a complex projective space, and the quotient is the C-star algebra of the complex projective space, quantum complex projective space of one dimension less, and the ideal, as I said, is the quotient. So this is I of Vn+1, this is C-star of Fn, and this is C-star of Fn modulo set minus. Okay. In particular, we get an extension of C-star algebras that, yeah. Okay, I wanted to highlight it, and now it's very green. Yeah,
so from this exact sequence alone, you can immediately compute K groups.
Yeah, also, yeah, of course. This is the other way to compute the K groups, yeah. Special case is, of course, n equal to 1. And in that case, we get that what was said before, that C of CP1Q, so the Podrosh sphere, is the minimal unitization of the compacts. And this also, we also know that this sequence splits. So And when we started working on this project, and I think still now, we had never seen a splitting for the higher extent or higher dimension versions of this sequence, but they do exist, and this will be the topic of this talk. And how we came to realizing that such a splitting must exist involves Kk theory. So I'm gonna now move to the second topic in this talk to tell you a bit more about to recall something about Kk theory and Kk equivalences. So this will be part 2, Kk theory, Kk equivalences, and splittings, and split extensions. So before I move to that, are there further questions on this graph algebra part of the talk? Doesn't seem so, but well, we can.
Everybody's happy.
Yeah, we can comment more on this later if just do as you did so far. You have been doing so far. Just interrupt me if necessary. So I'm not going to recall K theory. I also put K theory in the previous part of the talk without recalling it. I think we're all familiar with that. I will now recall briefly what the Kasparov's bivariant K theory is. And also I will briefly comment later on the Kunz picture that we used in our paper. So, well, Kasparov's bivariant K theory somehow unifies both K theory and K homology. And basically for any pair of separable C-star algebras, A and B, where B is also sigma unital. Then Kasparov constructed, I think in 1980, constructed a Z2 graded group. Kk-AB, that has the following properties. So if we put the first entry equal to C, then we recover the K theory of the C-star algebra. If you put the second entry, oh, I wanted to write B there, sorry, to be consistent. If we do Kk of A, comma C, then we get the K homology group of A. So this is the first nice feature. And we have, there exists an associative and bilinear product from Kki AB times Kkj BC into Kki plus J AC, and now I and J can be either 0 or 1 because we have a Z2 grading, as I said. And this product, known as the Kasparov product, recovers the index pairing between K theory and K homology. Moreover, any element in Kk-AB induces a map from Ki of A to Ki of B. Let's put 0 here, or I put J and plus J, okay. And Kk-BB is a ring. And the K theory and the K homology, well, the K homology and the K theory, I wrote them like that, are modules over this ring. These are all the properties of Kk theory, but the most important property well, it's the Kasparov product, which makes that Kk theory is computable. So you can use it to perform computer index type computations. Okay, and now comes the definition of Kk equivalence. This is something that was mentioned continuously in the title and in the talk. So two C-star algebras. A and B are Kk equivalent. And this is all sometimes also called K equivalent. For instance, there is a very nice paper by George Skandalis on it gives an overview of Kasparov's K theory, and there it's called K equivalence. But anyway, so these two C-star algebras are Kk equivalent if they're...
Tutto bene? Allora fra qualche minuto vengo giù.
Okay, Gianni is talking. You should mute. Oh, yeah. If there exists a two-element alpha in KKAB, so in the Kasparov group from A to B, and beta in the other one, so from KKBA, with the properties when we compose them using the Kasparov product. In one way, we get the identity on KKAA, or if you want the class induced by the unit of A, by the identity on A, which is then A itself as a module, but let's not go into the details. And the other way around, so if you compose B with alpha over, now over A, then we get the identity on the group on KKBB. So if you have two C-star algebras that are Kk equivalent, then in particularly, they have the same K theory and Kk theory groups. So two C-star algebras that are Kk equivalent cannot be distinguished by Kk theory. And we have several instances of this Kk equivalence. So I will give you some examples also to motivate this notion. So the first thing is that, for instance, if this is about some important results in K theory being actually Kk equivalences. So for instance, the complex numbers and C0 over 2 are Kk equivalent, and this is nothing but periodicity. And then you may know about the Thom isomorphism. So if you have a complex vector bundle over a locally compact X, then you know that the K theories of the total space and of the base space of the bundle are the same. But this is actually a Kk equivalence. So C0 of X and C0 of E are Kk equivalent. And this is the Thom isomorphism. And finally, a very nice example of Kk equivalence, which is another notion of equivalence that we're interested in when we do C-star algebras, is Morita equivalence. So Morita equivalent C-star algebras are Kk equivalent. It's actually, so Kk equivalence is a weaker form of Morita equivalent, weaker than Morita equivalence, sorry. Okay, so yes, and then the other thing that I wanted to talk about in relation to Kk equivalence is, it's also an example, if you want, of Kk equivalence, is the UCT class and Kk equivalence. I'm not going to spend an awful lot of time on the UCT class. I will just say that the UCT class is the class of C-star algebras that satisfy the universal coefficient theorem, of Rosenberg and I don't know how to pronounce it properly. This is a universal coefficient theorem for Kk theory, so that allows you to write Kk theory groups in terms of Hohmann, Ext, and Tor of K theory groups of those C-star algebras. So whenever you have an algebra for which this theorem, universal coefficient theorem, holds, we say that it's in the UCT class. So this UCT class contains many interesting C-star algebras. It contains all the commutative C-star algebras. Compact operators are inside the UCT class. And moreover, it is stable under extensions, meaning if two algebras are in the UCT class and there is an extension in the middle, the extension is also in the UCT class. And inside the UCT class, we have this important result, which is also due to Rosenberg and Chauchet, from 87. So let A and B separable in the UCT class. And suppose that they have the same K theory groups. Then A and B are Kk equivalent. So what does this tell you? It tells you that whenever you have two C-star algebras in the UCT class and you have an isomorphism at the level of the level of K theory, you can lift it to an isomorphism in Kk theory. So isomorphisms.
But sorry, this isomorphism is just abstract isomorphism, or is it induced by some map?
No, it's quite abstract. The proof is quite abstract. Yeah, it requires homological algebra arguments and the UCT.
Okay. Okay, thank you.
So the isomorphism in K theory can be lifted to isomorphisms, to Kk equivalences.
But okay, this is also the case for Kk equivalence. Yes, these classes are also abstract. These are not induced by some map, not necessarily.
Well, they're induced by Kasparov module, but figuring out which Kasparov module realizes the Kk equivalence may not be so obvious again.
No, but
in some cases it is, but like in the Morita equivalence case, it's obvious what module you have to take. It's the Morita equivalence.
But I think he's saying that you don't have a map between the algebras. You don't
have. Yes, exactly.
Yeah, it may not come from a map between the algebras in general. No.
Have some correspondence, but
exactly.
not a plain map.
Exactly.
I see. Thank you.
But so like with the Morita equivalences, it's some correspondence that implements it. It's also Kk equivalence, and then Okay. So this is just, this is an abstract reasoning. So if you have a two C-star algebra in the UCT class and they have the same K theory, then you know they're Kk equivalent. So in particular, this applies for, this applies to CPN, to C of CPNQ, because of the extension that I wrote before. So let me copy it. Oh, didn't work very well. Oh yeah. Okay, I'll try again once more. Yes. So because of this extension, because we said that the compact operators are the compact operators are in the UCT class. So if CPn-1 is in the UCT class, then CPn is in the UCT class because of stability under extension. So we can do induction because CP0 is C and get that all the complex projective spaces are in the UCT class. So by induction on N, C of CPnQ is in the UCT class. And since it has the same K-theory group of as C to the power n+1, or if you want, since it has the same K-theory group as its commutative counterpart, then they must be Kk equivalent. So it's Kk equivalent to C of n+1. So Kk equivalent to commutative counterpart, because those are also in the UCT class, being commutative sister algebras. But again, this just says that, that there is such a Kk equivalence, but it doesn't say anything about what this Kk equivalence may look like. Okay. I want to make a quick remark that this part of the Kk equivalence, this was known by work of Sergei Neshveyev and Lars Tuzet, so just a surname, Neshveyev. So where they consider quantum homogeneous spaces like the ones I showed before. So they're quantum homogeneous space for the formations of a compact, simply connected semi-simple regroup and a Poisson-Lie subgroup. I'm not going to go into details, but what they showed is that these homogeneous spaces for, so the map Q, sorry, let me write it like this, 0, 1, Q. So this gives a field of sister algebras, a continuous field of sister algebra, and all the fibers are Kk equivalent. So in particular, you get Kk, they have this result that gives you Kk equivalence between the non-commutative homogeneous spaces and their commutative counterparts. So this is this was done in 2011 using a continuous field of sister algebras argument, the proof of this Kk equivalent. So what the strategy we follow here is very different, and it relies on another notion, which is the notion of a splitting. So this takes me to the final part of the second part. So the relation between split exact sequences and Kk theory. Okay, so let us consider an extension of the form 0 DLJ E and B. And we assume that the sequence splits. So it means that we are looking at the right split extension. So there exists a star homomorphism S from B to E such that Q composed with S is the identity on B. So this is what is called a right split in homological algebra, because we have the splitting for the right map. And then there is an important result. Well, this is theorem. It's actually it's an exercise in Blackadder's book. So I'll call it fact. The element J, class of J, direct sum, class of S. So this gives you a class in Kk J plus B, direct sum B, E. So the reason for that is this J here is just a map from J to E. So this is a class in Kkj E. And the same for S. The splitting is a map from B to E. So this is also a class in KKBE. And then you can take the direct sum of this class. But when I say direct sum, I mean that I'm just writing them like a diagonal matrix. So this gives you a KK class from the direct sum C-star algebra of J plus B and the extension. And this element is a Kk equivalence. And meaning it, we said before that in order to show that a map is a Kk equivalence, it's not enough to show that it induces isomorphisms in Kk theory unless it's we're in the UCT class. But so there is an explicit inverse, which is requires two classes. One is called well, there is an explicit inverse alpha in Kk E of J plus B that composed with this map gives you the identity in the two possible way. So this we construct, this is constructed in various ways. And in our paper, we recall the construction and use mostly the Kunz picture of a Kk theory. So.
May I ask you a question?
Of course.
How far this fact doesn't hold if we assume that this section is only completely positive instead of being a star homomorphism?
No, then, so if you have completely positive, then you just get that the extension induces 6-term exact sequences in Kk theory. But you don't get Kk.
So the point of this fact is that this exact sequence becomes also split.
Exactly, yeah.
Okay, thank you.
Yeah, this is far more general. If you only have this completely positive splitting, this is, for instance, true for nuclear sister. Sorry, for nuclear. I'm right. Nuclear sister algebras, right?
Mm-hmm.
And that's a huge class. But having such a splitting here, which is a star homomorphism, this is a very strong condition.
Yeah, it's much stronger. Yeah.
There is a question on chat about this.
But K theory is split exact. Shouldn't this immediately imply that the K theory of I plus B are E isomorphic to and lead to Kk equivalence? I'm reading a chat.
Yeah, so this is precisely the point. So the fact that this isomorphism lifts to Kk equivalence is requires that, so isomorphisms in Kk theory only lift to Kk equivalences if you're in the UCT class.
Yeah.
Which we are here. So that's the argument indeed.
But that's more, that's even like, I mean, like more general. Like you don't need UCT, you just like need that you have a split exact sequence and you know like Kk theory.
Yeah, but
you obtain like in Kk, you obtain a long exact sequence in Kk. Like not in K.
Yeah. So this is also how the proof works of construct. So if you have the sequences split, that this is exactly split exact. So the way you prove that this inverse exists is by using split exactness of Kk theory. So
yes, exactly.
Yeah, this is exactly the argument that you would use.
Yes. So you don't need any UCT in this.
No, you don't. No, you just write the long exact sequence, and then that's also how the exercise is in Blackadder. So if you look, the hint is write a long exact sequence, and it doesn't say use split exactness, but that's exactly how you would do it. Yeah. But you can describe these maps quite explicitly. So we did it in the Kunz picture. You can do it in the Kunz picture, which we found nicer for our work, but it doesn't really have to be there. So basically, the maps you get are well, one ingredient is Q. So let's write it here. One ingredient in the inverse is a class of Q, so the class of the projection. This gives you a class in KKE, did they call it B? Yes. The other one is something then, the other class is, it's what is called pi S. this is a class in Kk EJ, and this is called the split homomorphism. The splitting homomorphism, sorry. So to construct this splitting homomorphism, to describe it to you, I want to use Kunz pictures of Kk theory. So we call them KKH-AB cycles. Then, of course, this group will be isomorphic to the Kk theory group. This is a pair phi plus, phi minus of star homomorphisms from A to the stable multiplier algebra of B, so K tensor B, such that phi plus of A minus phi minus of A is in K tensor B for all A in A. So in our case, we considered this map that I called EP. It goes from E to E, to K tensor E. It's just tensoring any element with a rank 1 projection. Here. And this actually, well, you can show that this is independent of the choice. At the end in the construction, the choice of rank 1 projection is not doing anything. P is a rank 1 projection. And then because we have the inclusion of the ideal J into E, there is a canonical map from the multiplier that we called RJ, from the multiplier algebra of K tensor E into the multiplier algebra of K tensor J. And now our quasi-homomorphism is a pair of 2 maps. It will be RJ compose EP, and then RJ compose EP compose S compose Q. So if you want, this is just a class of 1 S compose Q. If you will put them in a diagonal form and have the grading 1 minus 1. So if you use graded Kasparov module, this is a different way of writing this up. So I will just say with grading, for those of you that know how to write Kasparov module, this will be just that matrix that has 1 here and S composed with, Q, not B, S composed with Q down there. But you can do it in the, that's also, so when you use the Kunz picture of Kk theory, you don't have the gradings, you have just a pair of star homomorphisms. So this is a way of seeing this map, but the upshot of this is that whenever you have a split exact sequence of C-star algebras, and there are various ways, as I said, this follows from split exactness of Kk theory, there is an explicit Kk equivalence between the C-star, the algebra in the middle and the direct sum of the two. So what I wanted to say is that the inverse indeed is pi direct sum Q in Kk E J direct sum B is the inverse. And it implements this Kk. So when you multiply it when you take the Kasparov product with J plus S, you do get the desired Kk equivalence result. Okay, so our strategy, still have 10 minutes, we should rush. To prove Kk equivalence is indeed to construct a splitting for the exact sequence. So we're looking for a map here. So the first observation is that you can use the UCT. Again, it's a bit of a killing mosquito with a big bazooka or something, but it follows from the UCT and from some homological algebra argument that the splitting exists. And maybe I can say a bit more about that later if you want. You can ask me, but not do it now because I'm running out of time. But again, this is a very special situation because of how these algebras are. So these algebras have a vanishing K1, and here we have the compact operators, which is also very special C-star algebra with vanishing K1. So extensions are classified by the group KK1. So this all comes together in telling you that this extension is trivial, so it splits. So let me now talk a bit about the splitting. So as I said, it's crucial in our construction that we use the graph algebra picture. So the graph algebra picture is crucial in our construction. So let me, of the splitting S from C of CPN minus 1Q and C of CPNQ. So again, we identify them. This is C-star algebra with the corresponding graph algebras. So here I will write C of Fn minus 1. And here I write C of Fn. So now we move back to the graph algebra word. And let me also recall our graphs. So I'll write both graphs here. So let me maybe do this a bit smaller. Oh, too small maybe. So let me write the graph for Fn and the graph for Fn minus 1. So the difference, they all have this infinitely many edges between the vertices. The difference is that they have different number of vertices. So Fn minus 1, I will just call the vertices with V, denote the vertices with V. So we have V1, V2, blah, blah, blah. And then we go to Vn minus 1, Vn. And then we have all this infinitely many so we will denote the vertices with the letter V from 1 to n, and then I'll denote the edges with E, with the letter E. So here we have E1 to M, and now M goes from 0 to infinity. So it's a countable number of edges. And now for Fn, we have n plus 1 vertices. We call them Wi. And then we call the edges in the same way. So Fij, M in n, Ij goes from 1 to n plus 1. So these are the vertices and the edges. And the reason why I'm labeling, I'm setting up the convention on the labels is because we want to see what this map S does on the generators. So recall that the C-star algebras are generated by projections and partial isometries. So this algebra is generated by PVIs and the SEIJM. Again, I and J go from Ij from 1 to n and M in n. And the other one is generated by PW, K in general, but let's use I again, and SF IJM, and now here I and J go from 1 to n plus 1. So we want to see what this map does to this projection and partial isometries on the other side. So, well, it maps PVI to P omega I for I from 1 to n minus 1. And then the last one, so the one corresponding to Vn, is mapped to the sum of P omega n and P of omega, W n plus 1. So we have one extra vertex. So what we do is we take the last one of the last vertex of the smaller graph and map it to the sum of the projections onto the two last vertices. And then we need to check to say what it does on the partial isometries. And again, the behavior is different whether we're at the end of the graph or not. So S Eij M is mapped to S F Eij M if J is different from N. So if you're not going to the last vertex, so if you're not here. And in the other case, we do the same trick as before. So S E I N, then M is mapped to S F I N M plus S F I N plus 1 M. So basically, we are taking care of the fact that there is one extra vertex and infinitely many edges that go there by treating the last vertex on a different footing. So this is the splitting, and what we proved in our paper. So I should say A. Mikkelsen. Is that the map S from C of CP n minus 1 Q, well, maybe this deserves a label Sn, to C of CP n Q, defined as above, is a splitting for the short exact sequence here.
I think when it is a splitting is completely obvious. What is non-obvious is that is well defined.
Yeah, of course. This is what we proved, of course. Yeah, so first you need to check that it's well defined, and then that it splits, you see it from the from the relations in the graph algebra. So I'm not gonna give you the proof of this. It's well, it requires some, as I said, some computations, but in particular, this has the consequence that if this is the inclusion of the ideal, this is the projection, this is Sn, then we get a map Jn direct sum Sn. This gives you a class in Kk of compacts plus C of Cpn minus 1 Q to C of Cpn Q. And this map is a Kk equivalence. And the inverse is constructed as above using the splitting homomorphism. And this is this in particular has the consequence that because K is Morita equivalent, so up to Morita equivalence, because the compact operators are Morita equivalents to the complex numbers. So when you compose also with the Morita equivalence between K and C, we do get a Kk equivalence between C of Cp and Q and the complex numbers. So the sister algebra of n points. And proving that, so once you have once you have the splitting, this just follows from the split exactness of Kk theory. So you can prove it by just computing this Kasparov products, but they're there and they give you the right thing. And I see that I have 1 minute, so we'll just stop now. So this was the main theorem is indeed the construction of the splitting, and we found it, well, we already discussed this with Piotr in another occasion. This is quite surprising because such splitting do not exist classically between the classical counterparts, but they are there here. And this seems really to be a feature of the graph algebra or of the fact that there is this deformation going on.
And after discussing with you and Sophie, I discussed with Soren, and he is wondering about some if and only if condition. Just forget, look at graph sister algebras, look at some nice exact sequences of graph sister algebras, and he's wondering about some if and only if condition for such a splitting to exist.
I see, yeah.
So, that's
so what it means at the level of graphs.
Yes, exactly. Yeah. Exactly. This was a follow-up discussion to our discussion.
Yeah, nice.
Yeah, so that's very nice. And Francesca, please correct me if I'm wrong, but I understand the fact that these two sister algebras are Kk equivalent. That's trivial. This is obvious.
Well, it's a
the point is that this implements the Kk equivalence. That's the
exactly
point.
So that this splitting, that we use this splitting to implement it. It's and the fact that the splittings are there, it's also something that comes from the particular form of the extension. So we do think that this can be somewhat generalized to other graph algebras like the weighted projective spaces very easily, because there are difference there is that you have k to the power m, but the argument for the existence of a splitting still works. So this could be something that we will do next if we get a nice graph algebra picture of the weighted projective spaces.
Yeah. Okay, so
yeah, and that was about it. So I'll just write a thank you.
Thank you very much. Thank you so much.
Thank you for being here.
Where is my clapping hand? Here it is. Okay, so let's continue with questions, guys.
I have a question, if I could. Okay. If this splitting doesn't exist in the classical limit, and we know that this presentation is a deformation of the usual presentation of complex projective, classical complex projective spaces. Did you try to check what is happening in this classical limit with this splitting?
Yes and no. So I mean, I didn't look at the splitting explicitly, but what I did look at is try to mimic the homological algebra argument here. But here and it didn't work because instead of having the compacts, you have another type of sister algebra, and all my reasonings broke down there. But maybe what is worth stressing is that we couldn't write this, how do you say it? This splitting, we couldn't write it in the more commutative picture with the projections generating the sister, the entries of the projection generating the sister algebra. We really needed the graph algebra picture to write down the splitting. So we tried it by looking at the PIJs and it didn't work there. And again, I wonder if the problem there is the form of the explicit isomorphism. So between the two pictures, so the Waxman-Soibelman and the projective and the graph algebra picture. So this is, but like working with this ZIs, ZJs and the PIJs was not very effective for us.
Well, but it's doable, Tomek. I think that you are asking.
Yes. You can write explicitly everything in terms of Z generators.
Exactly.
And then you can ask what is the limit. Of course, it's not. So there must be some kind of blow up or something like.
Could very I see what you're saying there.
Thank you.
Yeah, there are some, singular behaviors in K-theory when you go Q equal to 1. This is completely standard. Do you remember the dimension drop effect?
Sorry, Piotr. There are no jumps in K-theory. No. There are jumps if you think about K-homology and cyclic homology or cohomology.
Sure. Of course, yes. I
if you take the pairing, drops. It's your paper. You remember?
Yeah, I know. I didn't say jumps in K-theory. I said dimension drops.
No, but I don't know if this is really related, but the Qs are very nasty because, like, when you try to do the deformation of the Dirac operators, I mean, that's K-homology, of course, but that creates problem with the compact resolvents because of the powers of Q diverging.
Yeah.
So I wonder if there's something analogous here. It seems that the Q is really, makes the two words quite different on
but this is kind of funny because when you are at the classical level, the splitting does not exist, but Kk equivalence still exists, but it's not implemented by the splitting. So somehow by going quantum, your situation in K theory becomes simpler, more regular, more down to earth, because the star homomorphism is the nicest thing you can get.
Yeah, exactly. So at the classical level, you have the Kk equivalence because basically you're attaching an N cell and this N cell.
And we are used that it happens the other way around. We go quantum and things that exist classically.
You get the compact operators suddenly.
and now it's the other way around. I wanted to understand this killing of a mosquito with a bazooka. Can we go back to this?
I think it's already here. Yeah.
Yeah. I'm somehow confused. So all that you know that. So what can you derive using UCT theory and general stuff without having the splitting constructor? So what can you know?
Yeah. So what you can know is what we wrote down this lemma, which I think could also be an exercise because it's really homological algebra. That if you have a separable, sorry, the wrong color. So the lemma, well, maybe lemma it's too big of a name, but if A is separable and in the UCT class, and K0 of A is free and abelian, and K1 of A is 0, then any 0 K direct sum of M, so M copies of the compact operators E, A splits. And the reason for that is that, well, you can, so if you use the UCT to compute Kk1 of A, this is M copies of Kk1 of AK, and now now you apply the UCT, so let me get the Homs and the X correctly. So you have two things. The first thing is that X of K0 of AZ is 0 because K0 of A is free and abelian. So there is no X in the UCT, and then this will be just be Hom of K1A Z to the power M to the power, well, direct sum M plus K0 of A 0, direct sum M, and here one of them is this vanishes, this is 0, so this gives you 0. So this tells you that every extension of A by direct sum of the compact operators is trivial. So it splits. So, but this is purely homological algebra, but it has to do with, well, this being free and abelian. So for other graph algebras, you have torsion, like so it wouldn't work anymore. And this is the other thing that is playing a role, that these algebras are vanishing K1. So they're very special algebras.
And what would happen if you would replace compact operators by C naught of R2?
Yeah, that's the thing. I cannot get such a statement. So that was exactly what I was wondering about. Yeah.
Yeah. Yeah, because this short exact sequence relating CPN and CPN minus 1, of course, you have it for Q equal to 1 as well, except that compact operators then become just C naught of R2n, right?
Yeah.
And that sort of part you still have. But it's not compact operators, it's C naught of R2. One is responsible for Morita equivalence, one is responsible for both periodicity. These are different effects.
Yeah.
But both effects are encoded in Kk. So the question makes sense.
Yeah, exactly. Yeah.
If I could comment,
go ahead, but show yourself, Tomek.
Show myself.
Yeah. No, it doesn't. We know you're here. We hear you.
Okay. Can you see me?
Yeah.
Yes.
Okay. So my comment is that maybe it's not entirely right to say that what was impossible in the commutative case, it is possible on the level of Kk, because it's not an analog of passing from the classical picture to the non-commutative picture, because Kk, even for commutative algebras, what you wrote here for Cp and Q also holds for CPQ.
Yeah.
CPN. Okay, for the classical space. So this space is undistinguishable from the point of view of Kk from the discrete union of n+1 points.
Yes.
Okay. So the price you pay for this simplification under this Kk equivalence is very high.
Sure.
Because you are comparing things which topologically are incomparable. Very different. Even on the side of non-commutative algebras, you have such phenomenon like O infinity, the Kirchberg algebra, O infinity, is Kk equivalent to complex numbers.
Yeah.
So this cost is high on both sides of this equivalence of this let's say quantization, Kk quantization.
Yeah, but yeah, well, I mean, I had thought briefly only about this argument, but maybe it's, I wonder what it says in this case for C0 over 2, because now I don't see why this would.
No, I have nothing against Kk equivalence. It's very, very nice. Yeah. For instance, it's a way of proving that this algebra being Kk equivalent to a commutative system algebra,
exactly,
okay, UCT and so on and so forth. So it's a valuable result, yeah. But it's not as strong as the results modeled on classical topology.
No, of course, yeah.
Far from being homotopy equivalence, something like that.
No, it's very different from a homotopy equivalence or from
These operations are discontinuous between spaces. These
exactly
correspondences are highly discontinuous.
Yes, yeah, that's what makes it hard to generalize to, well, if not impossible to generalize it to the commutative case. Because,
And Tomek, could you perhaps tell us briefly why this such a speaking does not exist in the classical case? So in other words, when I have a standard inclusion of CPN minus 1 in CPN, then there is no retraction.
Can I propose that I
stop sharing and we use a whiteboard? You can use cohomology with integer coefficients.
Okay.
And then, of course, there is an algebra map between cohomology rings in the opposite direction, being one-sided inverse.
So you just use
you can also use K-theory for n greater than probably 3. Probably, no, for greater than 2. you can use again K-theory, but for small dimensions, you have to use again integer coefficients in cohomology.
And when I say cohomology, we just plain
multiplicative
ordinary...
structure distinguishes these two abelian groups. So as plain
Theorem, right?
abelian groups, K-theories are the same, but as rings are completely different.
Yeah.
Okay. Yeah, and the ring structure, as we know, is lost when you move to CP and Q. It's replaced by something similar but different, some module structure,
the Kk
right?
ring structure, indeed.
Yeah. Yes, exactly. Okay, no, that answers my question. So I think we don't need to go to a whiteboard. Anybody else? Anybody else wants to come and ask a question? I don't see any volunteers, so let us thank Francesca again. Thank you so much. Of course, I'm biased, but this was an exemplary talk for me. I'm biased because this is my cup of tea, but I don't see any way how to give this talk in a better way. So I really appreciate it. It's absolutely great. I stop recording.